Hi, welcome back. This is going to be, I guess, lecture number 5 on metric spaces. Today, what we are going to do is we are going to talk about closed sets. Again, I do not know. In one lecture, I can cover everything because I want to give good examples so that you have some kind of confidence and intuitive ideas about closed sets. Okay, so let us see. So the way we want to define closed sets is by saying I want if XD is a metric space, I want to say a subset A of X is closed if its complement, that is X, remove A, X minus A, that is open. Do you get the definition? Yeah. A is closed if X minus A, complement of A is open. Now, this should make you think just because we associate open and closed with the doors, we may think either it is open or it is closed. Given a set, either it is open or it has to be closed. That need not be the case because there may be a set A which is not open and the complement is also not open. Okay. In that case, you cannot say anything. You understand that? Anyway, let us make a formal definition and start working at it. Let me set the timer. Yes. Okay. All right. So let XD be a metric space metric space, right? I have subset A of X. I say it's closed if X minus A, that is a usual, but modern notation is X minus A, and do not, I don't even write like this. This is X complement A. This is the modern accepted notation. Okay. So I will avoid this. I will always use this. And as far as possible, I will try to use X minus A rather than A complement if this is open. Is the definition clear? Right. Now you should contrast this, okay, with suppose I have a real number, okay, say real number system. You give me a real number A. Then I define what is meant by a rational number, right? Then I say A is irrational if A is not rational. That's it. It's a mutually exclusive. Given a real number, either it has to be rational or it has to be irrational. But that's not the way we work with open sets and closed sets. Given a set A, I say it's closed only if and only if the complement is open. Okay, right. Keep this definition. We will slowly get used to this. We will give a lot of examples so that you will understand this better. The first example is as usual, okay, in R. Let us look at R. Look at the closed interval A to B or A to infinity or minus infinity to B, any of these things. Okay, these are all called closed intervals. Notice that we don't put closed at infinity or closed at minus infinity because they are placeholders. This only stands for X greater than or equal to A. This stands for X less than or equal to B. That's it. This stands for X greater than or equal to A and X is less than or equal to B. Two conditions. Here there is only one condition. Anyway, so I want to say this is closed. Let us see. How do I say it's closed? Go back to the definition. This is closed in R. Okay. We will say, if you want to be precise, I may say closed in R, X. But that's not needed in general. Okay. I say it's closed in R if the complement. What is the complement? I have AB. What is the complement? Complement is minus infinity to A union B to infinity. Do you understand this? If when does X belong to R? If and only it satisfies two conditions. So, sorry, not R, AB. When does X not in AB? I'm just teaching a little bit of logic so that you also get to know how to work with this. If X is not in A, if X has to be in A, in the interval a b, it has to satisfy two conditions. Therefore, if x is not in the closed interval, then it does not satisfy at least one other condition. Therefore, either it is x greater than or equal to a is not true. In that case, by law of trichotomy, x must be less than a, or x is greater than b. You understand that? But this is the set minus infinity to a, and this is the set b to infinity. And since x can be, satisfy this condition or satisfy this condition, that means x may in the interval. Now, what do I know about this? We have seen any open interval is an open set. Therefore, this is an open set. This is also an open set. We had also seen arbitrary union, in particular finite union of open sets is open. Therefore, this is open. So what have we shown now? We have shown that this interval is closed because complement is open. Other cases are similar. For example, in this case, what is the complement? A infinity r minus. See, this means x must be greater than or equal to a. Therefore, the complement will be x less than a. That is same as saying minus infinity a. You know, that's what just now we saw. Okay, this complement is this. This is open, and similarly this case. Have you understood? Okay. Let us look at one or two cases now. Right now, let's look at set of irrationals. A to be set of irrationals. Now I want to know that it's closed. Remember, I already shown it's not open. Maybe it's closed. Can it happen? No, because I'm sure all of you remember, we also said this is also not open. Okay, and this is also not open. Right? So if this is closed, then r minus q must be open, but that's not true. And similarly, when I take b equal to r minus q, that is also not closed. Why? Because what is its complement? Q, but that's not open. Therefore, these are not closed. Yeah? Okay. Let us look at one more example. Suppose let us look at set of integers as a subset of R. How many of you see it's closed? See, these are the kind of thing you should learn to look at pictures and develop intuition. This is 0, this is 1, this is 2, etc. Minus 1, minus 2, etc. Right? I want to know whether it's closed. What is complement? The complement are going to be this kind of open intervals. You see that? So what are the complement? R minus Z, that is R complement Z, is union of, what does it start from? N to n plus 1 R base n varies over Z. Do you understand this? All open intervals. Okay. Now we know these are open intervals and hence open. And this arbitrary union, in fact, countably infinite union. But anyway, it's union of open intervals. Therefore, R minus Z is open. Right? So this way Z is closed. Yeah? Have you understood this? Okay. Now, before we go further, let me look at a very abstract example. Let X be any metric space. Right? I just want to see what happened here. And suppose this is my metric space and I have finitely many points. Right? Finitely many points. So my A, if you want, let me write it as x1, x2, xn, a finite set. Okay. Can you say it is closed? Can you see that it is closed? To show it's closed, what should I do? Look at x minus a. Okay, x complement a is open. That's what I have to answer. Now let's look at that. If you remove a finite set, take any point here, I can always find an open ball around this point which avoids any of these points. That is, this open ball lies in x minus a. Okay, it avoids any of these points. Can you see that? And you can put, it looks very, it could be like this. But still I can avoid. Even here I can put a small one, right? Okay, just to develop intuition. We are going to give a proof rigorously. So don't worry about that. Okay, so what is that I want to say? I want to say the complement of A is open. What does that mean? Give me an AX in x minus A then does there exist an R positive such that Bxr is containing x minus a, right? What does it mean to say B of x minus B, the open ball Bxr is containing? This happens, this is the crucial idea you have to see. If and only Bxr intersection A must be empty. Do you follow that? Okay. Now we will analyze when this is not empty. Suppose this is not empty. What does it mean? That means there is a y here. That means distance between y and x is less than r, and y also lies in a, right? Y lies in this, right? You follow that? And how many such points are there? So y has to lie in a, but y has to be one of the x1, x2, xn. You understand this? Please think. Yeah. So let us make a picture so that you will know this is my point x. Okay. And these are my points x1, x2, x3, x4, x5, x6, etc. Right? What I can do is I can find the distance between all of these things and so on, right? And suppose I take the minimum distance. So let R1, Rj equal to distance between xj and x. Okay. Notice that this is greater than 0. Why it's greater than 0? Because x is not in A, and in particular, therefore, x cannot be xj. Therefore, this has to be positive. Clear? Okay. Now, how many such rj's I have? I have r1 to rn, and each rj is positive. Therefore, minimum, if I take to be r, then r is also positive. We had already seen it earlier, right? Right. So, look at the minimum distance and take an open ball around that now. That's it. That's it. Okay. So, what do I do now? I look at bxr now. I claim this intersection is not empty. Sorry, it's empty. Why? Again, the same thing. If y belong to that, distance between x and y must be less than r, but y is in a, that means y must be some xj. Therefore, I get a distance between x and xj is less than r. But that is x. Remember that? This one. Distance between x and xj is rj. So it, okay. But this is less than or equal to rj. But this is rj. So what is the contradiction I get? Rj is strictly less than, because there is a strict inequality here. So I get the strict rj is strictly greater than. This is absurd. So this contradiction shows bxr intersection is empty. What does that mean? Given any x in the complement of A, where A is a finite set, I have found an open ball bxr which is completely contained in x minus a. It does not intersect A, is same as saying it's completely contained in x minus a. That means x minus a is open, because this is true for every x. Yeah. So pause, review, proceed. Okay. So this is the second example. Now let's do a third example, again in an abstract setting. Let xd be a metric space now. Right? You may remember we proved, in fact we used many times above, the open ball is always an open set. Okay, this is an open ball, it's also an open set. Now you may wonder, what is the next question you would like to ask now? Sure, I know all of you can say that. Is a closed ball a closed set? It's a very natural question, right? If open ball is open set, I want to know that closed ball is a closed set. Yeah? Well, it's true. We are going to prove. Let us. We do not know it's true or not. Okay, it's true actually, but I am going to prove. Okay, is it open? Okay. So let us look at this. This is my x. Okay. This is my bxr. This I want it to be circle, where this could be arbitrary, but it turns out like this. Okay, this is close ball bxr. Okay, so it's to just show it's a close ball. Let me say this is included. Okay, the close ball, right? Now this is my x and this is my y. Okay, so let dxy be greater than r. So call it, say it is r. Okay, right. Now you can see from the picture this is r, and okay, I hope all of you see this. This is r and this is capital R. So you can see this is r minus r. So it looks pictorially, I can go up to this. This could be radius r minus r, of course positive. Okay, I can take a positive radius around y. This must happen. Yet the picture suggests this thing. Do you remember the same way how I proved bxr is an open set? First picture we used, then we also worked backwards. Do you remember that? That's a keyword, work backwards. Okay. So what I want to know is whether there exists a row positive such that by row, okay, intersection bxr is empty. You understand? That would mean by row is contained in x minus bxr, right? That means given any arbitrary point y in the complement, okay, I can find an open ball which is completely contained in the complement, right? So we will work backwards. I want to know what kind of row. I already have an idea. My idea is that this may be less than r minus r, or equal to also may be allowed. Okay, but I can verify. But let us try to do working backwards, because that's one trick in mathematics you have to learn. Okay, suppose this is not empty. Suppose this is not empty. What does that mean? There exists z here, right? Okay. Now let us see. Now the only thing I know, the distance between y and x is equal to capital R. So somehow I have to see whether I can arrive at some kind of a contradiction. Okay. So let us look at that. Distance between x and y is less than between distance between x and z. Okay. And distance between z and y. You understand this? Right. Now, what is distance between x and y? This is capital R. That should be less than or equal to distance between x and z. Okay. That will be less than r, and this will be distance between z and y. This will be less than rho. Yeah, right. Okay, so what is that I want to know? Right, or maybe I can also do that. Let me see that distance between x and y is equal to r, right? Therefore this is r is less than this, right? That, what does that mean? R minus r, this is x and z. What is x and z? X and z, that is z is here, that is less than or equal to r, and this is distance between, this will be strictly less than r, therefore strictly less than, right? Okay, therefore r minus r, okay, should be less than rho. Is that okay? But that doesn't need, okay, this doesn't see get what I want, so let me abandon this, right? Okay, if that doesn't work, let us try something else then. Okay, so let us look at distance between x, y, n. Okay, yeah, so y and a, therefore distance between x and y. So distance between x and a, okay, sorry, distance between x and y is less than or equal to distance between x and z, okay, right. But suppose this is r minus r, okay, this is equal to r, right? Okay, yeah. So I'm sorry, this works, so let me do that. So distance between x and y, which is equal to r, but that is by triangle inequality, distance between x and z plus distance between z and y, okay. But distance between x and z, where is z? Z lies in bxr less than or equal to, therefore this will be less than or equal to r. Distance between z and y, z lies in this, therefore it will be strictly less than rho, but rho is r minus r. But that's strictly less than, therefore this is strictly less than, therefore the whole thing is less than this. Are you following? But that's equal to r. So we have proved r is less than r, so a contradiction. So what do you think I have proved? I have proved that if I take rho equal to even r minus r is okay, okay, then b y rho lies in x minus close ball b x r, right? This is true for every y. Therefore, b x r is closed set. Pause, review, proceed. Okay, next what is that I would like to do? Yeah. The next thing is, let us look at, this is for which example? Third. Okay, now let's look at a fourth example. Okay. Now suppose x and y are metric spaces. We have the product matrix x cross y, right? I'm looking at the set A. Let us look at the picture. This is my x, this is my y. Here fix a point A. Look at this set. This is the set singleton A cross y. This is a subset of x cross y. And with the product metric, right? Okay. I want to know that whether this is open, is closed. Okay. Right. How do I prove that whether this is closed? So what is that I have to do? This is closed in where? It's closed in x cross y. Remember, this is a subset of this, right? So what should I do? So start with any point x comma y not in A, right? That is x cross y minus A, right? X cross y minus A. This is this way, right? Okay. Then what do I have to do? I have to find an open ball bxy r which is completely contained in x cross y minus A, which is same as saying bxy r intersection A is empty. I have to find. Okay. Do all of you understand? Now let's look at, if I say xy is not equal to A, what is the meaning? What is A? A is singleton A cross y, right? Therefore, if x is not here, what does that mean? So, I mean, xy is not here. What does it mean? There is only one condition. If it is there, x must be in the singleton A. That means x must be A, and y may be any arbitrary element. Therefore, this happens if and only if x is not equal to A. Do you understand this? Yeah? Yes? Therefore, let us look at the picture. Therefore, this is my A, this is my x. This may be my xy. And this may be my x. Right? Now, remember, x is not equal to A, therefore there exists an open ball B x r, okay, which will not have A. Why? Because distance between x and A, if you call it r, this r is positive. All right? And if A belongs to this, simply means distance between A and x is strictly less than r. You understand that? Therefore, I have an open ball like this. I can even reduce it by half. That doesn't matter. Okay, take this. Now, I have found an open ball here, but I want an open set in X cross Y. What is the easiest way to do that? So therefore, there exists an R positive. Let R equal to distance between X and A. This is positive. Therefore, BXR does not contain A. You understand? Very good. Now what do I want to do? I want to find an open set which contains, this is my A, this is my X. I want an open set which contains, this is my XY. Right? I want an open set. How do I do that? It's very easy. Okay? You will be surprised. I can do something easy, but I want to do something like this. B XR cross Y times Y. Now this is open in X and Y is open in Y. You understand that? Yeah? Right. Therefore, and we had already seen product of two open sets and product topology is open. Therefore, this is an open set in X. Yeah? Very good. Now, what is that I have to prove? I have to prove U intersection my A is empty. Because I have to say this is an open set which contains A, right? Yeah. Or if you want, let me just, sorry, because you may want some open ball is what we want on to prove open set. Okay. Yeah. Let me just modify this definition because this is an open set is not enough because according to our definition, I am supposed to find an open ball around BXY and this may not be an open ball. You understand that? So I, but doesn't matter. Therefore so forget this, take to be BXR cross BYR itself. Okay. Then we know this is nothing other than B of XYR. Right? We have seen it in our product metric, right? Now again and again you can see why we spend a lot of time, one full hour to understand open balls in our examples. You can see it pays dividends to us now. Do you appreciate this? Very good. Okay. So I claim this U intersection A is empty. Suppose not. What does that mean? There is a point U comma V which is here. Right? But U comma V, A, that means it be, in particular is in A. Right? If it's not empty, then it belongs to U intersection A. Therefore, U comma V belongs to A. That means U must be equal to A because A is singleton A cross Y. Therefore, U must be, this is U, this is A. Do you understand this? Yes. But remember, this U V belong to this BXR comma BYR. But now I concluded my U is nothing other than A. Therefore, that says AV belong to BXR, this one. That means in particular A belong to BXR. This is a contradiction because we chose R so that A is not in BXR. Do you follow that? This is a contradiction. Therefore, we have said that this open ball BXR, sorry, BXY R, okay, is contained in X cross Y minus E. This is true for every XY in the complement. Therefore, this is open. And hence, singleton A cross Y is closed. Pause, review, proceed. So these are the things you do not see in general. But looking at these kinds of stuff makes you understand how to work with open balls, how to argue carefully. Okay, right. Now, what is the analogous question you can ask? I'm sure all of you are smart, so you know what is the next question I can ask. Fix a Y and look at this. This will be what? This will be X cross singleton Y or B if you want. Okay. So whether this is closed, what is your guess? Yes, it's closed, right? Okay, very good. Okay, so let me see what are the other things I can do. Maybe I should, oh yeah. Yeah, now let's look at, before we go further, let me look at an example to say that a set, given a subset of metric space XD, it need not be open and it need not be closed, right? That is, given an open set, say given a subset A, you should not say either it should be open or it should be closed. It may happen it is neither. The example is very easy. Let us look at, for example, A open at B. Yeah, right. Now is it, so is it open? No, because what is the source of point problem here? Why this is not open? Problem point is A, because take any open ball around A, namely open interval A minus R, A plus R, that should be completely contained in this. That's not possible, right? Because A minus R by 2, that will belong to A minus R to A plus R, A minus R by 2, but that is not in AB because it's strictly than A. Yeah, right. So it's not open. Maybe it's closed. If it is closed, what should happen? The complement should be open. What is the complement? Complement is minus infinity to A and then B to infinity. Okay, so the complement of this is R minus A, B is minus infinity to A. This is open, but then its union B infinity. Okay, now you say maybe this is open. Don't say this is closed. Of course this is closed. We know this is closed. Just now we proved it. And this is open. But it may still happen this is open. In that case, union of open sets will be open. So I hope to show this is not open. I hope to show this is not open. Do you understand this? Why this is not open? Of course, the reason is similar. If it is open, then there is an interval, open interval around B, which is completely contained B to infinity. As an earlier argument, that's not possible. Therefore, this is not open. Right? So, but B is a point in this set. And around that, I can't find an interval. Therefore, this is not open. See, what I have to prove, this is not open. You follow that? So start with this. B is a point of this set. It cannot be open. If it is open, then there is B minus R to B plus R. But these points are not in this set. Okay. Please pause, review, proceed. Okay, let me see what else I have to do. Okay. Now let's see, let XD be a metric space. Let's see be the family of all closed sets. Do you remember? Last time what did we do? We looked at T, the family of all open sets. Okay. We studied the properties. What are the properties? One was empty set is there and X is also there. And two, if U is an arbitrary collection here, the union U, okay, this is the notation. This stands for U, union, the script U. This is in, again open. And third thing was when U and V are in tau, then U intersection V is also in the topology, right? This is what we saw in the last lecture. So we want to see what are the analogous properties, right? So first notice that empty set will again be closed set. Why? Its complement is X, which is open. Therefore, empty set is both open and closed. And similarly, the full space X is both open and closed. Do you follow that? And next, okay, let us look at. See, now remember the basic trick is, how do I get closed sets? I get closed sets by complementing open sets, right? Right. So therefore, if I have a family of closed sets, let us say AI, okay, let me say script A, which is a subset of closed set. This is script A, okay, subfamily of closed sets, right? Now, you look at this. I said if they are open, this, okay, let me say, therefore, if a belongs to script A, what does it mean? Then U, let me define UA to be X minus A. This is open, right? The complement of A. You follow that? Right. Okay. Now what do I know? I know that union UA, A varies over C now. Oh, sorry. A varies over script A now. See, this is a family UA and it is indexed by the indexing script A. You follow that? Yeah. What do I know about this? This is open. That is, it is in tau. That is, it is in tau in the topology. Right? But I am not interested in this. I am interested in the complement of UA. What is complement of UA? It is A. Therefore, if I want this, what should I do? I have to take UA, A in script A and complement equal to what? This is by intersection. This is UA complement. A running over script A. But that is equal to intersection A running over script A. Right? Since this is open, the complement is closed. Okay. And I know many of you will have problem with this kind of arbitrary union, intersection, etc. Please go through this. If you have problem, I will soon release a short video explaining arbitrary union, arbitrary intersection, taking complement of all these things. Okay. Because these are things not taught. You know how to work with finite sets, okay, etc., or finite collection, but you may not know how to work with arbitrary collection. So there could be a problem. I will attend to that. But for the time being, we accept this if you want. Okay. So what have we shown that? We have shown that intersection A, as A varies over A, script A is a family of closed sets. Then this is again a closed set. Why? If to say it's closed, what should I do? Intersection A in script A, take its complement. But that complement is going to be, take the complement A in this script A. But this is UA, A in this. And US are open because A is closed. Okay. And arbitrary union of open sets is open. Therefore, this is open. Okay. Complement of this intersection is open. Therefore, the complement is closed. Okay. That's a proof. As I said, if you are slightly uncomfortable, wait for another video where I will deal with the set theory. And the next one is somewhat easier. Suppose A and B are closed sets. Then I want to say A union B is closed. How does it follow? Again, it's because of that. See, here what did I do? I took arbitrary union, but closed sets has to be something with complement. Therefore, complement of union is intersection of complement. That's what prompted me to prove arbitrary intersection of closed sets is closed. Now, look at this. What does it say? We have, okay, intersection of two open sets is open. So if I have to take complement, then what will I do? Union of two opens to union of two closed sets will be closed. That's the correct thing. You follow that? So we are going to prove that. So let us look at A union B complement. This we know is A complement intersection B complement. Yeah. But what do I know about A complement? Is A is closed, therefore this is open, and intersection of two open set, therefore this is open. Therefore this is correct. Okay. Please go through this As I said, do not lose heart if you do not understand either this or the corresponding this. Okay, there is plain set theory. In a way, another short video I'll explain these things. In fact, I should have done it when I did union of open sets, but I thought students may be able to follow. But anyway, okay, before we stop the lecture, yeah, I have another 10 minutes, 12 minutes. So I want to introduce a new way of thinking. Okay, suppose I give a set A in X metric space. What does it mean to say A is not closed? I want to understand this. Okay, and A is not closed is same as saying U, which is X minus A is not open, right? So to say A is not closed is equivalent to saying its complement is not open, because that's a definition. You understand? So I want to understand when A is not closed, which is same as saying U is not open. Okay, let us see. U is not open. What does it mean? If U is open, what is the meaning? For every X in U, something must be true. What is true? There is an R positive with the property BXR such that BXR is contained in U. You understand this? This must be true. So if U is open for every X, let's not worry about what this is. This something. This is something. Okay, some statement. This statement is true. So if U is not open, what does it mean? At least there exists one X in U for which this is false, right? That means there is X in U, something this is false. Whatever is it, this is false. This does not happen. Okay. What should happen? Given my S, I should be able to find at least one R so that BXR is contained in U. That is false. What does it mean? Give me any R positive, then BXR is not in U, not contained in U. If BXR is not contained in U, what does it mean? I have U, I have X, and BXR is this. That's not contained in U, meaning there exists at least one point. When do you say A is not contained in B? There exists an X in A, so that X is not in B. You understand? Right. Therefore, if you say BXR is not contained in U, there exists a Y. So there is, okay, there exists X in U, so that for every R positive, there exists a Y in BXR, so that Y is not in U. But Y is not in U. What is U? U is a complement. That means there exists X in U, so that for every R positive, there is a Y in BXR, so that Y is in A. Okay, what does this mean? This means there exists X in U, so that BXR intersection A is not empty for every R positive. Okay, pause, review, proceed. So let us go slow. I will repeat, but it's best that you learn it. If A is not closed, then if and only if its complement is not open. Let me understand when it's not open. If it is open, what does it mean? For every X in U, something happens. That must be a true statement. That is, I should be able to find an R positive so that BXR is completely contained in U. If that is false, that means there is at least one X for which this I cannot do that. So suppose I take an R, then BXR cannot be contained in U, because then it will be true. It is not true. That means give me any R, BXR is not contained in U. Okay. So when BXR is not contained in U, what is the meaning? There is at least one element Y in BXR which is not in U. But what is U? A complement. Therefore, where does this Y belong to? It belongs to A. That means give me any open ball centered at X. Okay. I can always find an element of A inside that open ball, which is same as saying if A is not closed, Okay, that means there exists an x not in A. You understand? Where is x? X is in U. Therefore, if A is not closed, there exists x not in A, that is x is outside A. So that give me any open ball BXR, it intersects A. Okay, it's quite a mouthful. Let me formulate. Please think over this. So what you have shown is this. You have proved this. If A is not closed, then there exists an element in X but not in A. Right? So that every open ball BXR centered at X, okay, intersects A. That is, every open ball intersection A is not empty. Have you understood this concept? Yeah. So if this is not closed, this is what it means. Okay. Please pause and review. I am trying to push you learning much better things, slightly more subtle things. Okay. These are all logic. The problem is the logic. That's why you'll have problem. So go slow. Discuss with your friends. Okay. All right. Therefore, such points are very important point. Okay. So we are going to make a definition now. Okay. Let A be a subset of a metric space X and let X be a point in X. I say X is a limit point. Okay. This is not the standard definition of limit point. If you had already gone through a course, your definition of limit point will be much stronger than what I'm saying. Okay. So sometimes I write it as limit point and K is silent as in knife, as in night. Here K is silent. Okay. So since I pronounce this as a limit point, I will only write this way, like Americans, right? If you don't use this word, why unnecessarily write that letter, right? Okay. Just for fun, mess. Okay. Yeah. Right. Look, this is a limit point if for every R positive, PXR intersection A is not empty. That's all we did. You see that? If A is not closed, then there is an X in this, so that every open ball intersects A. Okay, those balls are very special. See, these are something like this. See, look at this. This is a picture. Okay, I take any open ball, however small, you can see it has to intersect A. That means it is kind of sticky points. These points X, okay, they stick. That is, some point of A has to stick to any point of. Think of BXR. Okay, this is an adhesive tape. X is there. Then always I can find however small like adhesive tape I take around X, there will always be a point of A in that. Okay. So if you want, you can also call sticky point of A. Anyway, you understand this definition? Yeah. So I say it's a limit point of A if for every R positive, BXR intersection is not empty. Just to make sure you understand, let's look at the interval AB. Okay, take this point A, take any interval. Whatever be the radius, you will see it always a point in the interval AB. And take any point C, it will have. Yeah. But notice that I am not saying it must have a point of A other than X. If you learn limit point definition elsewhere, you may get confused. I am not insisting. The point which is common to this may be X itself. Right? Okay. The last one I forgot. I don't think we did discrete space, right? Let XD be a discrete metric. Okay. Let A be a subset of X. Is it closed? Remember, We have seen that in a discrete metric, every subset u of x is open, right? Therefore, when is A closed? If x minus A is open. But this is an arbitrary subset of x, therefore it's open, and hence every set is closed. Therefore, in a discrete metric space, okay, every subset is both closed and open. Okay. So this is the definition of limit point. Therefore, what you have shown is if A in X is not, see, I'm digressing. This was a digression because I forgot this example. So I just now remembered, but I'm going back to the original thing. So A is not closed implies what? There exists a limit point x of A so that x is not in A. That's all we proved. Okay. Let us look at that. If it's not closed, there exists x which is not in A, but then it intersects every point. If any x in capital X, any open bar intersects A, then I decided to call x as a limit point of A. But I say this point x is not in A. That means if A is not closed, implies there is a limit point of A which is not in A. This is the theorem we have proved. Okay. Please pause, review, proceed. And this way of thinking may not be found in general textbooks, and even in my book this is okay. So it will be good if you go through this and discuss. Okay. In the next lecture we will see why I want to call this a limit point. Okay, not the standard definition of limit point, but I would like to call this a limit point. Okay, when we deal with convergence sequences in the next lecture. Okay, and also we are going to show a subset A of a metric space is closed if and only if it contains all its limit points. That's the theorem we want. So the final theorem is this. See, we have characterized this. Okay, see, remember now we have two definitions, equivalent definitions of a closed set. One is A is closed if complement of A is open. Now this one, okay, see, somewhat intrinsic. What does it say? It says it's a closed if and only if x is the limit point of A, x must be in A. Okay, we shall prove that because it's already about 15 minutes. I think that's, and since these are the lot of subtle things I have done, I don't want to push you hard. This should be good enough. Okay, please review and pass your comments below the video, and because I have that kind of feedback to me. Okay, if you had some difficulty in future videos, I can explain the difficulty, or I can release a separate short video to clarify that issue. Okay, so please feel free to pass your comments. Have a good day.